You have a handout called Practice Exam Questions, and this video is aimed at very quickly going through some of the answers for those questions. So let's have a look at that right now. Question 1 asks you to sketch 2 cycles. So there's 2 cycles of a sinusoidal supply. It doesn't have to be pretty, but do 2. If you do 1, you may not get the marks. And you're asked to mark on there 4 things: amplitude, RMS, period, and peak to peak. So let's do that quickly now. So RMS is, if this was 0 to 1, then it's about 0.7. So something up here doesn't have to be spot on. So RMS is 0.7071 times Vmax. So that's that one. Try and indicate it as clearly as you can on your sketch. Amplitude is from the midway point to the top. So that is amplitude. Could have left myself a little more space. Amplitude, squeezed it in. Period. You could mark period almost anywhere, but I'll put it from there to there. It's the time taken for 1 complete cycle. So period. And that just leaves peak to peak, which is from the top of one peak to the bottom of the next. So that is peak to peak. Okay, can't remember how many marks that was for, but there you go. So hopefully you've got that one done okay. So let's move on. Let's have a look at question 2, periodic time. So part A, T equals 1 over F. And if you put the numbers in, that's 1 over 50. Work it out, that is 0.02 seconds. Or if you prefer, you might write 20 milliseconds. Both of those would be acceptable answers. Part B, frequency. It's the same formula. F equals 1 over T. The T and the F just swap places. So put the numbers in. 1 over, the period was 10 milliseconds. So that's 10 times 10 to the minus 3. And that will give you 100 hertz. Very short and simple questions, maybe worth 1 or 2 marks. Okay, question 3. How to generate electricity. You're going to need coil, magnet, and movement. All words very, very close to those. And if you rotate a single coil within a magnetic field, it will produce a sine wave. Okay, so hopefully your marks are building at this point. Question 4. You have to calculate RMS. Give me the formula. VRMS is 0.7071 times the maximum, or the peak, however you want to call it. Either are acceptable. And if you work that out, I'm hoping you're going to come to 230 volts. May actually be a tiny fraction different, but that's basically what the answer is aiming for. I hope that makes sense for you. So let's carry on. That was 4A. Let's have a look at 4 part B. So 4 part B, the RMS is 0.7071 times Vmax, and we're going to transpose that. The maximum is what we want, so move this away, it goes underneath there. So Vmax put the numbers in, and it was 110 divided by 0.71, and that will hopefully come to 155.6 volts. Okay, so that takes us to question 5, which I've already made a start on just to speed me along. So question 5 is all about heating. So on part A, you've got to explain what convection is basically, and here is a simple diagram. Here is a room, panel heater, and the hot air is going to come out of the top. It's going to circulate around the room and it will be cooling. So it's cooler until it travels back and it's cool, and that will go in the bottom of the heater. That is convection. So you have to describe things in words, which is a skill. You may need to practice this a little bit more. Okay, so I've tried to keep it simple with bullets. The heating element warms the air around it. This rises. Cold air is drawn into the bottom. So heat rises, cooling the bottom. The warm air circulates around the room, cooling as it does so. Final step. The cooling air falls lower into the room and is again drawn into the bottom of the heater. So I've just described that process. And I've said this is convection. It could be that in the question or in the member of staff, their answer sheet, it says you must use that word. May not say it at all, but often that is the case. So that's 5 part A. Okay, so I hope that sort of makes sense for you. Let's have a look at 5 part B. And I haven't written part B and C out. I'm just going to say it verbally. And you've got the time to pause the video and watch it and go through it again if you want. So part B was about storage heaters. Let me just invent something very quickly as we go through right now. So a storage heater uses cheap rate overnight electricity. During the night, large heating elements heat up thermal bricks which store the heat. Vents are opened during the day to allow air to pass through the heater and to heat the room by convection. So that's the sort of description that you'd need to write to get the marks. Part C of the same question, so that was 5B, now on to 5C. A 2-bar heater, and note in the question I called it an electric fire. That was deliberate, not the best terminology. It's a 2-bar heater. Emits heat by radiation. The infrared waves warm up people and objects nearby. That's all you need. So moving on to question 6. So let's move away from 5 and on to 6. Again, to speed us along, I've partly answered question 6. So it's about different parts of heating systems. So I've said a motorized valve. 6A, a motorized valve uses a small motor to open or close a valve which controls the flow of water in a heating system. When the room cools, the thermostat calls for heat. In other words, it's turning on the thermostat. It turns the valve on and supplies hot water to the radiators. Final step. When the room heats up, the thermostat turns off. It closes the valve to stop the flow of water. Again, that is perfectly adequate. You can write it in your own words and possibly explain it better than I have. So 6B and 6C, I haven't written it. Again, I'll do something sort of loosely verbal on it right now. 6B, room stat. Okay, so a room thermostat is used to regulate or control the temperature in a room. If a room cools down, the thermostat turns on. It's calling for heat. If the temperature rises, the thermostat turns off and it's said to be satisfied. Okay, the last bit, programmer. A programmer is an electronic device that turns on the boiler through and the hot water and central heating at different times throughout the day. Most programmers have two channels. One channel is hot water, the other channel is central heating. All right, so that'll do for that. Nice and short and sweet. And that takes us all the way to question 7, which I've just started. But in question 7, I think you're asked to explain where each of these voltages would appear or what they were used for in our electricity supply system. So 230 volts is domestic. So general appliances such as kettles, television, toaster, whatever. 400 volts could be light industry. Could also be offices. Could be schools, colleges, etc. And give a couple of examples if you're asked to do this. Or answer the question specifically. Probably say give an example or give 2 examples. 11 kV. So that's usually distribution around towns. Um, 11 kV distribution around towns. It could be a small hospital. It could be a large factory. So large factories. 33 kV is heavy industry. Things like steelworks, oil refineries, car plants, etc., etc. 132 kV is the national grid. .400 kV is the supergrid. Okay, so hopefully that's all right with you. Let's just move on. I think we're up to about question 8, are we? So question 8. Why do we transmit at such high voltages over things like the lines on the pylons down the countryside? Well, one reason, it keeps the current small. So on the conductors that run over the pylons, they have a small current in them because we're using high voltage, and that's because of the transformer equation. Okay, so we had to give 2 reasons. So that would be power loss. Keeps power loss low. Again, in the overhead conductor. There we go. So that'll do for that one. Right, so number 9. So question 9, I think I've started that one as well. I did. So question 9 is about transformers. And I've started the first question. So part A, sketch of a core, a shell and a toroid. And you would expect to label the primary on each one. Primary and the secondary. So secondary on this one, secondary, and then on this one. That'll do. Okay. So that's part A. Part B, we're into calculations. And you've got to find the secondary voltage, and you need the transformer formula. NP over NS is VP over VS. You could use the ratios at this point, but I'll work through using the numbers that were given. 2000 turns and 200 turns. Primary voltage was 240, secondary voltage VS. So if you work that out, that's 10 equals 240 over VS. Oops. So this needs to move to the top, so that's going to go up there, and that is going to come back underneath there. So VS equals 240 over 10, which is 24 volts. Okay, so that's 9 part B. Oh, there's a part C. 9 part C, 3 losses. 3 losses in transformers. Eddy currents, iron losses, and hysteresis. Okay, so we're getting there. I'm only going to go to question 10 in this lot, and I've started question 10. So you're asked to sketch and label and identify a star connected transformer and mark on it the nominal voltages. So I've just sketched this out. That's all you're going to do. You're going to have to draw it properly and label it. So the star point goes to Earth. Tell me, that is the star point. And then we would have L1, L2, L3. So what I really need, oops, it does ask for the voltages. So from the end of any line to the star, that is the phase voltage, VP, and that equals 230 volts. From the end of, oops, that went wonky, from the end of any 2 lines, that is the line voltage, VL, and we expect 400 volts. So that's just disappeared off there, apologies. So that's 400 volts. So these are the nominal values, the values that we use in general calculations, and we know they can vary a little bit. So, swiftly moving on. 10b, you have another calculation to do. So it's about a star system, and you need the formula VL equals root 3 VP. Put the numbers in that you know. So root 3 times 110. Root 3 times 110 will give you 173.2 volts. So that is the line voltage if 110 is the phase voltage. The final step there is, it says find the currents if the line current is 20. So in star, IL equals IP. The line and phase currents are the same, and you were given the value of 20 amps. So tell me that. Okay, the last bit for now then, again this is about supply systems. So part C, you're asked to explain a PEN, whatever that is, and a PME, whatever that is. So again, if you dip into your notes, PEN, protective earth neutral. A protective earth neutral conductor runs from the start point into a premises. It enables one conductor to be used as both earth and neutral. Check your notes, it's in there. PME, protective multiple earthing. The electricity supply company connects several conductors to earth along the route of the PEN conductor. So I'll do a very high speed scribble. Here's the transformer somewhere out in the street, badly drawn, but we have your PEN conductor and what the let's have a somewhere inside the premises, and that will split, but I'm not bothered about that. And what the supply company do is they put multiple earths along the route. So that's what protective multiple earthing is. Okay, so rest of the questions are going to follow on the next vid. Good luck with that.